Many of the materials we make use of in our everyday lives are types of polymers. These are found in nature or can be created synthetically in the lab. Some low-tech examples of polymer usage can be seen in this modern car. Made up of over 50% polymers, it is lighter and therefore more fuel efficient than the earlier metallic variety. Polymers are replacing metal alloys like steel and aluminium alloy as the main components in the body and chassis of today's vehicles. This is leading to lower production costs, and car exteriors that are now more aerodynamic and less prone to scratch and dent. Your safety is improved by the use of polymers in cars. An example of this is laminated glass in windscreens. Between two layers of glass in the windscreen lies a thin layer of the polymer, polyvinyl butyriol. In an accident which causes the glass to fragment, pieces of glass will tend to stick to the strong plastic polymer layer, minimizing injury and decreasing the likelihood of anyone being thrown from the car on impact. A polymer is a large molecule comprised of repeat units called monomers. Monomers can add together to form linear chain-like molecules, or may branch off, forming more complicated structures. Many polymer chains are bound to each other by weak intermolecular forces, forming a variety of materials, such as hard plastics, flexible rubbers, soft fabrics, and liquid coatings. What is even more exciting about these polymer chains is their ability to conduct electricity as metals do. Recent and ongoing developments in the world of high technology involve using conductive and semiconductive polymers in mobile phones, laptops, and television screens. Polythiophene are examples of conductive polymers that have proven incredibly useful in recent years in a series of high-tech applications. Here is a molecule of the most basic form of polythiophene. The monomer unit is shown in brackets. One polymer chain could contain many hundreds of repetitions of this monomer unit. Polythiophene is made up of carbon, hydrogen, and sulfur. These lines between the atoms show where they are bonded to each other through the sharing of negatively charged electrons, with each line representing a single bond, or a pair of electrons. The wealth of double bonds in the structure of the molecule allows for free movement of electrons along the polymer chain. The material is said to have delocalized electrons, imitating the chemistry of metals. Hence the nickname synthetic metal is given to polymers such as this. Conducting and semiconducting polymers threaten to replace other interesting types of polymer in television, computer, and mobile phone displays. LCD stands for liquid crystal display, and you're probably staring at one right now. Despite their name, liquid crystals are neither liquid nor crystalline solid, although they behave a bit like something in between, runny like a liquid but structured like crystals. Lots of rod-shaped polymers in a liquid crystal phase will form a naturally ordered crystal-like structure. This alignment will be affected by electric current or temperature change. Chemists have learnt to exploit these properties. Remember mood rings? No, it doesn't know how you feel, but the liquid crystals inside it respond very slightly to changes in your body's temperature. The changing configuration of the polymer rods affects the wavelength of the light that is absorbed by the liquid crystal, which has the effect of changing the colour that you see when the temperature changes. The new generation of display is the OLED, Organic Light Emitting Diode. Thin, light and flexible, the OLED allows for the possibility of giant flexible monitors, which would use even less energy than today's screens. Polymers are key to these devices. OLEDs rely on a process called electrophosphorescence, which basically means light will be emitted when electrons are transferred from one polymer layer to another. Here is the cathode, which will emit negatively charged particles, electrons. This is the anode, which the electrons will be travelling towards. The flow of electrons is what we call electricity. The two layers of polymer lie sandwiched between anode and cathode in a tiny electric circuit, 200 times thinner than a single human hair. The electric current is passed through the layers, sending a flow of electrons from the top emissive layer through to the bottom conductive layer. As the atoms in the emissive layer lose electrons, they become excited. In other words, they have more energy than usual. When an electron is received where it is needed, there is a trade-off of energy. The atom accepting an electron in the emissive layer will give out a photon of light, which is of the same energy as the electron it has received. Once the light has been emitted, the atom's energy is as before, and the whole process may begin again for that atom. Although there are examples of naturally occurring polymers, for example cellulose in plant cells, and protein chains in DNA, many of the polymers useful in high technology are synthetic. Every polymerization reaction takes place in 3 steps: initiation, propagation, and termination. The initiation step requires an initiator. The example given here uses free radicals, molecules with unpaired electrons. During propagation, carbon atoms from different monomer units will bond to each other. This is facilitated by the carbon-carbon double bond in the original monomer. The monomers will keep adding to the growing polymer chain until the reaction is terminated. Chemists today have great control over these experiments, allowing them to dictate the structure and size of polymer chains, and therefore design compounds with properties perfectly fit for specific roles. Nathion is useful in hydrogen fuel cells. These fuel cells offer a brilliant solution for powering cars and buses without using up precious fossil fuels and without producing carbon dioxide. Hydrogen and oxygen gases are pumped into the cell on either side of an electrical cell. The current ionizes the hydrogen molecules into electrons and protons. This is where the polymer nathion comes in. It is used as a selective membrane which can be permeated by protons, shown here as positively charged hydrogen ions, but will not permit transference of electrons. The hydrogen protons are permitted passage through the selective nathion membrane, whilst the electrons, which cannot pass through, are sent around the electrical circuit that runs around the outside of the cell powering the circuit. On the other side of the cell, oxygen atoms combine with the hydrogen ions and the electrons from the external circuit to give the product water. What makes nathion the perfect material for this application is the ability to conduct protons. Here is the polymer nathion. This highlighted group of atoms form sulfonic acid. The nature of this site in the molecule is highly acidic, and the highlighted bond will break very easily, freeing a hydrogen ion to move on to another identical site. Thus, a flow of positive ions is maintained. In this application, nathion is described as the proton exchange membrane, giving the PEM fuel cell its name. Some predictions for the future. Bigger and brighter OLEDs could be used to light our houses more efficiently than ever. Perhaps 100% biodegradable polymer cars will become available to the public. Hydrogen fuel cells will increase in popularity once the expensive nathion has been replaced by polybenzimidazole. Hopefully, more polymer materials will continue to replace metals in the production of lightweight, low-pollution automobiles. And one thing's for certain, where there's technology, there will be polymers.